Okay, so I guess we got to take a quick quiz. Let's see here. Um, see here. Okay, how about we say number one should be find partial z partial x and partial z partial y if f of x y is equal to z is equal to x cubed y cubed minus 2y squared x squared plus xy minus pi. And then let's see what our number two is. Oh, hope you're doing okay, computer. Ooh, good news. So let's wrap this quiz up in like a minute or two. All right, let's turn them in. Thank you, guys. Talking about 11.5 today, but before I do that, I want to make a note about last class period. I had written this. What was it? Minus b. So I had written this, and Ivor was wondering, shouldn't that be x, y? And I was just like, no, of course not, because my dyslexia had kicked in and I switched a, b, and x, y. Yes, absolutely, this needed to be x, y. I'm treating this as a function in the variables a and b, and that's not true. A and b are constants, so this needed to be like so. So that, thank you for being patient with my slip-ups, guys, and thank you to you students that catch my errors and are paying attention. Thank you very much. All right. So yeah, that was an error from last class. I need to get it together and sleep more. I need to just tell people who keep wanting to talk to me on the streets, hey, Professor Niels, I can't talk to you. No, I have to go to bed. I just got to be mean about it now. I just gotta say no to people, guys. You gotta learn to say no to people. Who here has that issue? Is it hard for you to say no to people? Is it hard for you to say no to people? Sometimes. Yeah, for me, typically it's not, but sometimes when it's your family, it's very hard to say no to your family. So yeah. You gotta know how to say no to people, one. Two, you gotta realize when you make a mistake, fix the mistake and move on, learn from it. So some life lessons here. Let's move on to 11.5, the chain rule. Okay, here we go. Okay, so recall back in Calc 1, let's say we had a function f of x defined as multiplication of two functions, h of x and g of x. Recall, to take the derivative of f of x, you had to do this. Remember what this rule was called? That's right. It was called the chain rule. And so if you had some y, which is equal to a function of x, the differential way of doing the chain rule is you said, you know, dy dx is like your dy over dt, your dt over dx. Okay, so that's like the Leibniz notation of it. dy dt here. Okay, let's do this right. This needs to say dy dt, and so I actually want my dt here. I want my dx's to cancel. Okay, so that means my y, I erroneously put it to be, it needs to be a function of t. That's just one example, okay? So let's talk about what if you have some function z, which is equal to some f of xy, and your x is a function of t, and your y is a function of t. Okay? What does it mean to take like dz dt? Okay. So note that dz dt, okay, this is going to be equal to partial z, partial x, partial t, plus partial z, partial y, partial t. So you see that the partial x's cancel, and the partial y's cancel, if you will. And again, actually, I wrote z, but you could also call it f. Your book calls it f, but don't forget f is z, so it really doesn't matter. I'm going to erase it so it's consistent, but it really didn't matter. The way I had it was also something that's valid. So we're going to be doing the chain rule here. We're going to talk about it in general, and then we're going to apply it to situations. So let's say z, for instance, is equal to x squared y plus 3xy to the fourth. Let's say we say x is set equal to sine of 2t, and y is set equal to the cosine of t. All right. So we aspire to find what is the total derivative dz dt. Total derivatives are with capital D's. Partial derivatives are with lowercase deltas. Okay. So just like so, dz dt, I have the total derivative is equal to this stuff. So what is partial f partial x? It's this guy, z. That's why I had z, because, you know, this is your f. This is your f of xy. It really doesn't matter. So still, partial x of this function is a 2xy plus a 12xy cubed. And then what's partial x, partial t? That's when I take the partial derivative with respect to t of my x. The derivative of sine is cosine. But then we got to do the chain rule, partial t of 2t, right? So that means this equals 2 cosine of 2t. So that's this term and this term. Let's find the other two terms. Yes.
The partial f, partial x, shouldn't the last term, if you're taking partial derivative?
Yes. I'm taking partial derivative of y. Yes, thank you. Good catch. So yeah, it's as if I was taking partial y. That's not accurate. So 3y to the fourth. Thank you, Jamie. 3y to the fourth. Seems like you're paying attention as well. Good job. Okay, so now let's go with partial f, partial y. So I'm taking partial y of f. Over here, it becomes x squared. Over here, now this is what that 12xy cubed. All right, and then last but not least, Where can I fit it? I'll fit partial y, partial t over here. Let's see, that's the derivative of cosine. Derivative of cosine is negative sine. Yeah, we could have a partial t of t here, but that's just 1. So know that that is secretly there. It's just trivial. So I won't put it usually. Now, this ends up becoming this thing times this thing is 2 cosine of 2t plus this thing, x squared, times this thing, x squared plus 12xy cubed. There you go. Okay. So sometimes they won't just ask you what is partial z, what is the total derivative of z with respect to t. Sometimes they'll say, okay, find that and then find partial z, partial t, such that t is set equal to some value. All right. So for instance, why don't we just set t equal to 0? It's a very nice value. And let's see what we'll get for our output here. Okay, so all we need to know is x and y. All the other pieces of information can go away. So this can go away, this can go away, this can go away, this can go away, this can go away. Okay. So remember, x and y are functions of t. So I can say, okay, if t equals 0, then x transforms to sine of 2 times 0, which is sine of 0, which is 0. And if t is equal to 0, y is equal to cosine of 0, which that means it equals 1. So our y is equal to a 1, our x is equal to a 0. And here in this result, any, oh man, this doesn't seem right. Why my error checkers didn't find something here? This shouldn't say that.
It's the second one is negative sine t.
Yeah, that sounds right. Thank you guys. Boom. All right. So that's partial y, partial t. Correct? Yep. All right. So now, what we're going to do is replace x with 0, y with 1, and t with 0. So this becomes 2 times a 0 times a 1 plus 3 times a 1 to the 4th, close, and 2 cosine of 0 plus x is 0 plus 0 minus sine of 0, which is 0. This whole thing becomes 0. This becomes a 1. This becomes a 0. So this reduces to 3 times a 2, which is a 6. So 6 is equal to dz dt such that t is equal to 0. If we set t equal to some other constant, we start from here, replace what x and y equal, and then replace t values and then compute. Okay, let's do a chemistry problem. Speaking about applied mathematics, is anybody in here interested in grading for Dr. Neuenswander? You get paid for it.
I don't have time.
You don't got time? You don't have time? You guys are very busy students. I understand. Just gonna pitch that idea out there though. Okay. So one of the gas laws says that PV is equal to nRT, but then N and R can be solved for in this situation to give me 8.13 T. Oh, again, dyslexia strikes. 31, not 13. So P, T, and V stand for pressure, temperature, and volume. All right. It says that, okay, the rate at which the pressure is changing when the temperature is set constant to 300, okay, it's in Kelvin. It's increasing at a rate of 0.1 Kelvin per second. So 0.1 Kelvin per second. That's equal to partial T. Temperature in the numerator, time in the denominator. All right, then it says, okay, this is for temperature being 300 K, but for volume being 100 liters, it's saying that the rate 0.2 liters per second is the change, positive, an increase of 0.2 liters per second. So that's a change in volume versus time. So we get a partial temperature, partial T, partial volume, partial T as our pieces of information. So we notice that from this equation here, that P is a function of V and T whenever you solve for P. See that? So I could just say P is equal to 8.31 T times V to the negative 1. Okay, so then I can say dP dt, the total derivative, is the partial derivative of V and T with respect. So you'll see what I'm saying. So you're going to get your partial P, partial T, no, partial P, partial your V, partial your V, partial T. Okay. And then now you're going to get your partial your P, partial your other variable T, partial your T, partial your little t. Okay. Recall, we have the numerical values for this term. It's a number. And we have the numerical values for this term. It is a number. All we have to do is now calculate that partial P, partial V, and that partial V, partial capital T. Let's do it. Partial P, partial V is the derivative of this guy. So if it's with respect to V, it ignores this part. So this becomes 8.31 T. It's treating that like a constant. And it takes the derivative of this, so it becomes negative 1 times V to the negative 2, partial V of V, which is just 1, right? So then this reduces to partial P, partial V reduces to negative 8.31 T over V squared. Next, let's compute partial T, partial little t. No, no, I mean partial P, partial little t. Okay. And actually, I mean partial P, partial capital T. Okay, so then let's take the derivative of this guy with respect to T. Notice it just perceived 8.31 over V as a constant, and it's just partial capital T of T. That's just 1. So look, we just get till we get here. All right. So now, don't forget we defined t to equal 300 and v to equal 100. So when I rewrite this, partial p partial v is negative 8.31. It had a t, but why don't we just plug 300 Kelvin in there? Divided by v squared, but why don't we just plug in 100 liters in there? Okay. Times this partial v partial t, which we have given, is 0.2, plus partial p partial t is over here. It's our 8.31 divided by our v, which is 100 liters, times our partial capital T partial little t. That ends up becoming right there our 0.1. Okay. So this checks out to be approximately this implies that the total derivative, the change in pressure with respect to time, is approximately negative 0.0415 kilopascals per second. So that's really cool. You have like a gas inside some container, and you can get this information, and you can find out that, okay, this is the change in volume is this, and with respect to time, and the change in temperature is this with respect to time. Then how can we predict the pressure will change? Then you'll see that you can calculate things like that using mathematics. All of engineering is math, guys. All of engineering is applied math. All of it. All of chemistry is applied math. Because all of chemistry is applied atomic and nuclear physics. And atomic and nuclear physics is applied theoretical physics, and applied theoretical physics is, guess what? Applied mathematics. Not trying to say we're at the top, but you guys seen that little cartoon in the math department where it's like, hi, I'm a psychologist. And then after that, it's like, oh yeah, well, we're biologists and we describe you. And then the chemists are like, oh yeah, well, we're chemists and we describe you. And then there's physicists and they're like, oh, we're physicists, so we describe you. And all the way down at the bottom, it's, oh, hey, we're mathematicians, we describe the rest. But technically, more pure than us are the philosophers. But who cares about them? All they do is think about questions that can't be answered. Oh, I think the meaning of life is this. Oh, well, good for you. Go test that. Can you test what your meaning of life is? No. So, okay, I'm not interested in hearing what you have to say. You're sitting there talking for like years, writing books from the bottom of the floor to the sky, but you didn't discover a thing. You just wrote down what you were feeling. All of your books are just like diaries or journals. Get out of here. Let's get something done. Let's practically get something done, guys. I'm hating on philosophy a little bit, but it has its own place in the world. So given f of x, y is equal to z, and let's say our x is equal to some g of t, our y is equal to some oh no, let's switch it up. Let's say, okay, let's define our variables like so. So f of x, y is equal to z. X is now parameterized in terms of a function whose variables are s and t now. So x is a function of s and t. Y is a function of s and t. So if we want to find what is dz dt or dz ds, what does that mean? Okay, and I like to put dollar signs through the S because, you know, S's and 5's can kind of look alike. So what does this look like? Partial z, partial t. What is this talking about? Well, we're going to have to apply the chain rule, okay? So this is going to be your partial z, partial s, partial s, partial, no, this is wrong. Partial z, partial x, okay? Partial x, partial s, plus partial z, partial y, partial y, partial s, okay? That's what that becomes. See, I was trying to say partial z, partial s, but z is technically not a function of s yet. That's why we call s and t intermediate variables, okay? So to respect that they're intermediate variables, you can't write it out like that. So then this becomes partial z, partial x, partial t, plus partial z, partial y, partial t. So just know if your function z, f of xy, and f of xy and xy are functions of two variables, now you get two possible chain rules here. Let's apply this to a situation. Let's say we got z is equal to e to the x sine of y. And let's say we got x is equal to st squared. Y is equal to s squared t. I had a math teacher one time, he was hella German, and he wouldn't say squared, he would be like squared. So sometimes I say it like that. Hopefully it's not distracting. Well, let's find partial z, partial s, and what is this equal to? Let's find partial z, partial t. What is this equal to? Okay, I deleted it, but you guys can easily derive that. Partial z, partial t is equal to partial z, partial x, partial z, t, plus partial z, partial y, partial t. So let's find each of these pieces. Partial z, partial x is taking the partial x of this. Partial x, partial t is taking partial t of this. Partial z, partial y is taking partial y of this. Derivative of sine is cosine. Partial y of y, which is 1. We don't write that. We omit it. And then we say partial y, partial t. That's partial t of this, which is just s. See how? So this results with, I get e to the x sine of y times 2st plus e to the x cosine of y times s squared. That is all for that one. Let's find the other one, partial z, partial s is the same thing as partial z partial x partial s plus partial z partial y partial s. So let's find these terms. Partial z partial x is partial x of this. Partial x partial s is partial s of this, which is just t squared. And then partial z partial y is partial y of this. Derivative sign is cosine. And partial y partial s is partial s of this, which is 2. Okay. So then this reduces to e to x sine y times t squared plus e to x cosine y times 2st. Pretty straightforward. Not that bad, eh? Just a lot of computations. So I'm not gonna do a problem like this because we're running a little low on time. But technically, you would be able to apply this to many variables. This is a 2-variable situation. Let's say you have 4-variable situation. If I erase something you were trying to write, just know that the videos are going to always be published, so you can always fill in your notes that way. What if z is equal to a function of x, y, w, and t? What is the total derivative how do I actually want to like denote this? Let's actually x, y, z, t, that's much more intuitive. X, y, z, t. Okay. Now let's call this one w. All right. Let's say that x and y and z are functions of uv. All right. So then what is dw dt? Or actually, what is partial w, partial u, partial w, partial v? I mean, any of these questions can be asked. But let's discuss partial w, partial v, and partial w, partial u. Okay, notice that this becomes partial w, partial x, partial v, plus partial w, partial y, partial v, plus partial w, partial z, partial v, plus partial w, partial t, partial v. That's what the chain rule becomes. Over here, you get partial w, partial x, partial u, plus partial w, partial y, partial u, plus partial w, partial z, partial u, plus partial w, partial t, partial t, partial u. So just know, that's what's going to have to happen. If you have a function of multiple variables, and you have these intermediate variables, u and v, for instance, this is how the chain rule expands. I won't do a problem having to do with that. It's hairy and messy. Takes too much time. Now let's talk about implicit differentiation. Again, talking about implicit differentiation again. So, given some function, okay, and given the fact that we can express y as a function of x across some domain, meaning that now we have f of x like so. Notice that we can actually say take the derivative of both sides of that. Okay. v dx of 0 is 0. Now we get d capital F dx, right? But what is that? Oh, applying the chain rule, that's partial f, partial x, partial x, partial x. I know. And that's partial f, partial y, or your f of x, partial y, partial x. Notice that anything divided by itself is 1. Or you can consider that as partial x of x, which is also 1. That piece turns into a 1. Notice that then we can solve for partial y, partial x. And actually, it then becomes a total derivative, not a partial derivative. It becomes a total derivative because it's in one variable. There's no mixed variables. Recall, why is that the case? Because y is a function of x. Because we can define y implicitly across a domain. Peep the implicit function theorem for why that is possible and mathematically valid. So then you get negative partial f over partial x divided by partial f over partial y is equal to our dy dx, which is our y prime. So this right here is how you do implicit differentiation with partials. My goodness, man. Class is already over. That's okay. The only thing I didn't get to do is define this for 3 variables, which is a luxury, and apply it to a problem. So you guys are going to have to fill in those details on your own. Welcome to college. That's how it is. They're like, oh, you're expected to know the rest of the material when you get to cover in class. That's how it is. It's not because we hate you. It's not because we're mad at you. That's just how college works. I posted homework for 11.4 and 11.5. Okay. If you guys need more time for any of those, just let me know. If something happens, just let me know. Don't abuse that kindness, but yeah. Those deadlines are more to like make sure you have all your stuff finished before the test. If we don't create deadlines as instructors, like students tend to like, not you guys are very responsible. Other students, you know, freshmen, typically like leave it to the last minute, and you can't do all this math at the last minute. It's impossible. So stay up to date with your work. And you guys already do. I'm preaching to the choir over here.